Motion on an inclined plane or ramp. Here in part 1, we'll be looking at smooth ramps, meaning frictionless. In part 2, we'll see how the addition of friction modifies things. Our ramp is inclined at an angle theta with respect to the horizontal. Theta, the Greek letter for I think the Greeks were really onto something when they had one letter to represent instead of two. And I, for one, think we should have kept it. And then we could be writing things like Thelma, the math sloth. And that's a world I'd like to be living in. Oh well. So 3 key ideas we need for motion on inclined planes. 1, our step AAA, align your axis with the acceleration, means it's a good idea to tilt your axes. Take your ordinary XY axes and tilt them to line them up with the ramp. Step 2, the normal force exerted by the ramp on an object sitting on the ramp is not equal in magnitude to the object's weight in this case. It's going to be less than the weight of the object. We'll see why when we look at the FBD. And 3, friction are reduced on inclined planes because they depend on the reduced magnitude of the normal force. We'll come back to that point in part 2. All right, let's apply our 3-step dynamics strategy to motion on a plane. Step 1, FBD. So let's put some box on a ramp here and look at the interactions it's experiencing. I see 2. 1, it's interacting with the planet Earth via the force of gravity. There's the weight of the box. And 2, it's interacting with this surface right here, which is exerting a contact force perpendicular to the surface, so that's the normal force. Here, the normal force is not vertical, it's tilted because it has to be perpendicular to our surface, which is tilted. That brings us to step 3, aligning our axes with the acceleration. I've got my free body diagram redrawn here, and since we know that the box will be accelerating either down the ramp or it could be pushed up the ramp, it's accelerating in this direction. We want our axes lined up with that direction. So instead of ordinary XY, we tilt them to get those axes right there. And part of this step, after you've chosen your axes, is to then look at your free body diagram, look at your forces, and see which forces line up with your axes, like the normal force does with the Y direction, and which forces do not, like gravity does not align with either the X or Y directions here. So a force like that, we need to break up into components. And here we'll need a component that is parallel to the Y-axis and one parallel to the X-axis. So we get a right triangle with the original force as the hypotenuse. So aligned with the Y-axis, here is our Y component of that force, and then here's the X component of that force. Let's label those. This is FGY right here, pointing in the negative Y direction, and then FGX here, pointing in the positive X direction down the ramp. Once you've broken your force into components, we then need to do a bit of geometry to analyze this triangle. So we'll need your standard geometric principles here of Euclidean geometry. Opposite interior angles are congruent, vertical angles are congruent, supplementary angles add up to 180, and complementary angles, as in the 2 non-right angles of a right triangle, add up to 90 degrees. Putting those ideas together, we can draw diagrams such as this, one big triangle here, which is analogous to our big ramp right here, and a little triangle right here, little right triangle, which is similar to our components of our force of gravity triangle right here. Looking at which forces are congruent in this picture can help us interpret our free body diagram right here. So whenever you're working with an inclined plane, it's useful to refer back to this image to work out which angles are congruent to which. Let's work through that now. Here, I see a sort of a medium-sized right triangle right there, and I can tell that this angle must be congruent to that angle, and then by opposite interior angles, these two are congruent right there, and that makes this angle complementary to that angle, and since that's the same as that, then this angle here, it turns out, is congruent to our original angle down here, theta. And we've concluded that this is also equal to theta right there. In this diagram here, we'd be saying that this angle is congruent to that angle right there. And that's the key we need to continue the analysis. At this point, bring in your standard trig functions here, and note that sine of theta is equal to fgx over fg, cos theta is equal to fgy over fg, and that brings us to the last step of AAA, which would be to then use trigonometry to express fgx and fgy in terms of the angle. So fgx is fg sine theta, fgy is fg cos theta, and then using Newton's law of gravity, we can replace the magnitude fg with mg, so fgx is mg sine theta, fgy mg cos theta. Now we've completely broken down our free body diagram here and are ready for Newton's second law. Newton's second law shall be applied in component form. One equation for the x components, one equation for the y components. We'll expand each sum of forces as the sum of the x components of all the forces, the sum of the y components of all the forces. So I recommend that you always state N2L, write N2L on the page and underline it, and then we can write AX, acceleration in the x direction, is the sum of the x components of all the forces over the mass of your object. We're stating Newton's second law for the x direction, and then we write our terms in our sum of forces here. There is, in the x direction, only the x component of gravity. That's it. There's nothing else pulling in our x direction. So it is fgx that's going to accelerate that mass down the ramp. And we already showed from the trigonometry that fgx can be written as mg sine theta divided by the mass. Mass over mass cancels out. Masses die off. It's mass murder. And we're left with g sine theta as an expression for the acceleration in the x direction down the ramp. Now go to the y direction, ay, and we restate Newton's second law, but here we know that we have zero acceleration in the y direction. How do we know that? Because whatever we put on the ramp is not going to levitate off the ramp in that direction, and it's not going to sink down into the ramp in this direction. It's only moving along that axis. Therefore, we're in equilibrium in the y direction, no acceleration in the y direction, which means that the net force in the y direction, sum of the y components of the forces, is, what are the terms? There's Fn in the plus y direction, Fgy in the minus y direction. So Fn minus Fgy, and those must be balanced, so that sums to 0 right there. Fn equal in magnitude to Fgy. I like to put bracket around those two equations there to sort of organize our Newton's second law. And one more step to conclude right here. Let's rewrite that as Fn, our normal force, is equal to the y component of gravity, which we already showed from the trigonometry is equal to mg cosine theta. And that's the second conclusion we need to fully understand how an object is going to move on this ramp. Let's look at those. Ax is g sine theta. That's our acceleration, and here's the strength of the normal force. That's our apparent weight. And from looking at these two terms and understanding how sine theta grows from 0 to 1 as your angle goes from 0 to 90 degrees, and cos theta goes from 1 to 0 as your angle goes from 0 to 90 degrees, we can picture how the acceleration and the normal force both change as your ramp tilts to ever greater angles. Our acceleration increases as your ramp tilts higher and higher. Of course, that makes sense. That is our sine theta function increasing as you go to bigger and bigger angles. But the normal force decreases in magnitude because of our cosine function here decreasing as we go to ever higher and higher angles. So that's our apparent weight getting smaller and smaller as the ramp tilts more and more. The ramp is pressing less and less, holding up less of the weight, supporting less of the box as the angle gets greater and greater. So for our extreme cases here, if the ramp isn't tilted at all, a horizontal surface, then sine of 0 is 0, we get no acceleration, and cosine of 0 is 1, so the apparent weight is equal to the ordinary weight. The normal force is just equal to mg if we're flat surface. If we tilt all the way to 90 degrees vertical surface, then sine of 90 is 1, our acceleration is g, we're in free fall. On a vertical surface, your mass is just going to fall straight down. And the normal force is supporting none of the weight then. 90 degrees, cosine of 90 is 0, so Fn is 0. Our object is going to be weightless. One more thing to look at, how much force is going to be required to hold the box in place if we don't want it to accelerate down the ramp. If we didn't want it to slide down the ramp, we'd have to push on it. We'd have to push upwards, up the ramp. And how big would our applied force have to be? Well, it is Fgx right here that is accelerating the box down the ramp. So we have to apply a force up the ramp equal to Fgx to ensure no acceleration and our box stays at rest. So an applied force that big so that this is equal in magnitude to Fgx right there to guarantee that we don't slide down the ramp. So we would have to have our applied force equal to Fgx, and from the trig we showed that's equal to mg sine theta. And since sine theta increases for greater angles, for a horizontal surface, no applied force is needed. The box will stay in place by itself. But for a vertical surface, then you'd have to be supporting the full weight of the block because the vertical wall wouldn't be holding up the block at all. So to hit again on one of our main points here, the normal force being mg cos theta, since cosine theta is always between 1 and 0, or it's a number less than or equal to 1, this here is telling us that our normal force is always less than mg, which is the weight on a ramp.